So ketone bodies and acetyl-CoA. I hope I convinced you with sort of this slide and this discussion that there's two main sort of pots we have for fuels. We have hydrophilic circulating fuels, for which glucose is kind of the gold star, if you will, for that. And then we have hydrophobic storage fuels, for which triglycerides are kind of the moneymaker for that, largely because we can pack so much energy into such a small space. So what's beautiful about ketone bodies is they kind of live as a hybrid between these. Okay, because the problem with carbohydrates, even though they're great because they are a circulating fuel, we are limited in the reserve that we have. We don't have an unlimited reserve of glucose. We do have a fairly limitless reserve of lipids. And what's kind of neat with ketone bodies is they can live in this space between, because we can have a fat-derived but hydrophilic circulating fuel. So we can kind of have the best of both worlds. So just a really brief slide here to remind us of the structures of these three different ketone bodies, remind you that they are ultimately synthesized from acetyl-CoA. We're going to get into sort of that synthetic pathway in a little bit. But if you have fat-derived acetyl-CoA, you can hook those acetyl-CoAs together and you can make these 4-carbon ketone bodies, which are beta-hydroxybutyrate and acetoacetate, and then the 3-carbon sort of decarboxylated version of that. So those are the three structures, but as a way to kind of organize them a little bit differently, I'm going to sort of put acetoacetate in the middle here. And I'm going to draw them as skeletal structures here just because it's a bit easier to sort of draw them. So here's acetoacetate. And again, when we have an excess of acetoacetate, this can be problematic because this can cause a life-threatening drop in blood pH. This is what we're going to call ketoacidosis. So that can be problematic. So a couple of things to think about in terms of these. This is synthesized from acetyl-CoA. Okay, so we're going to have 2 acetyl-CoAs essentially get zipped together. It's not just that simple. There's quite a bit of chemistry that's involved. But the net is to take 2 acetyl-CoAs and make them into acetoacetate. A ketone body that you might hear a lot about is beta-hydroxybutyrate. Okay. So beta-hydroxy, move myself over here a little bit, beta-hydroxybutyrate, okay, BHB, okay. This is basically just the reduced version of this. So if we reduce it, we are going to essentially get beta-hydroxybutyrate here, which reduces that ketone to an alcohol. So acetoacetate and beta-hydroxybutyrate are interconvertible by redox chemistry, right? So that's what this is. This is really redox chemistry. And then this is an important pathway here because we can take excess acetoacetate and we can decarboxylate this. This is a beta-keto acid, so it fairly readily decarboxylates without the need for sort of that TPP B1 vitamin that we sort of need if we've got alpha keto acids, but we can sort of decarboxylate and we can generate acetone. Now what's important about acetone is volatile, so it can be exhaled out. So as you have somebody who is in a state of ketoacidosis, they've got excess levels of acetoacetate. So one of the ways that your body can try to get rid of that excess acetoacetate is convert it by decarboxylation to acetone. Acetone being volatile, you can breathe it out in your lungs. So just kind of a brief introduction there to think about ketone bodies, highlighting that there's sort of this hybrid mix of the best of both worlds in that they are a hydrophilic circulating fuel. So we don't have transport issues or things like that like we have with lipid derived fuels. But again, because they are derived ultimately from lipids, they can tap into that unlimited reservoir of energy.